All right, so here we are now in chapter 19, amino acids and proteins, nearing the end of the course, moving definitely into that biological chemistry realm from our organic and biological chemistry second semester focus. So here we'll talk about amino acids and proteins, and again, just mainly their general features, and then in the later chapter lectures, we'll go into more details. So as I said, we'll focus this lecture on the proteins and amino acids, obviously coming off of amines and amides. This is the perfect topic, the biological macromolecules that are containing those two functional groups, as well as carboxylic acid groups and other side chains. So here we get to really pull it all together and apply all those organic and biological chemistry concepts we've learned to date, and learn the rest that you'll need for whatever your future entails. So here we talk about the function of proteins, and again, the proteins perform many different functions in the body. That phrase there could not be more of an understatement. We are what we are because of the proteins, as well as the carbohydrates we talked about earlier, and the lipids we talked about a couple chapters ago, and then of course the nucleic acids we'll talk about in the final chapter. But mainly, at least in terms of what all of that's moving toward, the lipids do provide some support for things like cell membranes, as we discussed, and of course the carbohydrates provide us with short-term energy, and all of it really comes together because of these proteins. And we see the different classes of proteins here in this table. We have structural, contractile, transport, storage, hormonal, enzyme, protection. These are really varied functions, and all very important, obviously, to maintaining a healthy human body. So I won't go ahead and read the table to you. Obviously, you can do that, but hopefully I can impress upon you just how varied the different types of proteins and their functions are, and how important all those functions are for life as we know it. So after looking at those functions of proteins and hopefully not getting too overwhelmed by that, let's start at the beginning. Let's start at the amino acids that make these proteins. So amino acids are the building blocks of proteins. Their name gives a lot of information, actually, right? They contain a carboxylic acid group, that's the acid part, and an amino group on that alpha carbon. So there's a carbon that is bonded to a carboxylic acid group, and that same carbon is bonded to an amino group, and that's what characterizes amino acids. They also are ionized in solution, so they're not these neutral things that we show. If you look at the bottom left, it looks all well and good there, but in reality, sometimes the amino functional group is protonated. Sometimes the carboxylic acid group is deprotonated. It just depends on the particulars, mainly the pH of the solution. And in the human body, the pH does vary. If we're looking at the gut, the stomach acid pH there, you're going to have mostly all protonated carboxylic acid groups and mostly all protonated amine groups. If we're looking at the intestine, where the pH is quite high, then you're going to be looking at probably mostly neutral amino groups and mostly deprotonated carboxylic acid groups. So it really is highly variable, just like the functions of the proteins themselves. So there are 20 common amino acids found in human proteins, and it's that R group, the side chain, that's denoted by R. That can be as simple as a methyl group there, as we see in alanine, or even simpler yet, glycine, it's a hydrogen. So that R group is what identifies those 20 common amino acids and what distinguishes one from another. So we already mentioned the ionization of amino acids briefly, but again, at the pH of most bodily fluids, amino acids are ionized. It's very rare that you would find a situation where neither the amino group is protonated nor the carboxylic acid group is deprotonated. That's quite unusual in physiological bodily fluid pHs. So the carboxylic acid group, being an acid, donates an H plus to the amino group to give a carboxylate COO minus, and an ammonium group from the amino group, an NH3 plus. That ionized form is called a Zwitter ion. My German is not where it should be, so I apologize for any mispronunciation there, but that's as close as I'm going to come after all my years of chemistry. What it means is that it's both a cation and an anion within that same original molecule, right? It's no longer a molecule because it's charged, but that formerly neutral molecule that we draw at the bottom left is now a cation and anion, and that's quite important for the functions that amino acids can do, not only the proteins that they make, but the amino acids themselves. So in addition to the amino group and the carboxylic acid off of that alpha carbon, we also have the R groups off of the alpha carbon to consider. And so amino acids are generally classified according to those R groups. So if the R group itself is nonpolar, then it's going to be considered a nonpolar amino acid. Obviously, it has polar functionality there at the carboxylic acid and amino groups. Those are both polar groups. But if the R group is something like a benzene ring, then the overall polarity is going to be nonpolar. They're going to behave as hydrophobic, and it's not going to matter so much about the amino and carboxylate functional groups. We can also have polar neutral amino acids. That means they have the oxygen and sulfur atoms but no charge. So those oxygen and sulfur atoms are fairly electronegative, and that gives rise to the polarity, but they're not going to gain a full positive or negative charge, at least not the side chain. Therefore, they're polar and hydrophilic, so they love water, but they're not charged. We can also have a polar acidic side chain, so that would contain carboxyl groups, negative charge as a result. Things like glutamic acid would have, in addition to its carboxylic acid on the alpha carbon, the R group off the alpha carbon could also have a carboxylic acid group at some point in that, at the end, obviously, because that's how carboxylic acid group appear, but it doesn't necessarily have to be right off the alpha carbon. So those are polar and hydrophilic as well. And then finally, we could have a polar amino acid that's basic. It could contain additional amino groups in addition to that amino group that all amino acids contain. The side chain could be or contain an amino group, and therefore could acquire a positive charge, and in acidic conditions where it would be protonated. So it would also be polar, also be hydrophilic. So we have lots of possibilities for polar hydrophilic and still nonpolar, and that's going to influence how the proteins fold, as all proteins are likely to have at least some of each type of amino acid. When we're dealing with a fairly large complex protein, it's quite likely we're going to have at least some R groups that would fall into each of these different classifications. Okay, so to follow up, we have some examples here. So as we said before, nonpolar would have hydrocarbon side chains. So they'll be hydrophobic, whether they're benzene type rings or even just a simple alkyl group like we see here with alanine, which has the CH3 group as its R group. It's going to be a nonpolar type of amino acid. If we look at a polar neutral with polar side chains, obviously hydrophilic, so something like serine there that we see to the right would be a polar neutral. It has a CH2 group and then a hydroxyl group, so it has an alcohol functional group on its side chain, and therefore it's polar, but it's not going to acquire a positive or negative charge on the side chain. Of course, as we see, the amino nitrogen is protonated there and has a formal positive charge. The carboxylic acid group is deprotonated and has a formal negative charge as carboxylate. But the side chain itself is neutral, just like the nonpolar alanine. The big difference, of course, is although it's neutral, it is polar because it can hydrogen bond in the case of serine. If we look at the polar charged R groups, we can have negatively charged, like aspartic acid, which has a CH2 group on the alpha carbon, and then off of that CH2 group we have our carboxylate group, which is negatively charged because at the pH that we're looking, it has been deprotonated. And then finally we see lysine, which has 4 CH2 spacers, and then finally that amine group there that is charged, a protonated ammonium now for lysine. So you have, in those cases, for aspartic acid, you have 2 negative charges and 1 positive charge, right? Because all of these amino acids are likely to be positively charged on the protonated ammonium and negatively charged on the deprotonated carboxylate group, but you get another negative charge on aspartic acid, you get another positive charge on lysine under most conditions. Of course, there are always ways outside of the body that we can manipulate things, and certainly inside the body unusual conditions may occur as well, but typically these are the ways that these amino acids would appear. Okay, so taking a chance to reiterate this one more time and look at the examples of the common hydrophobic nonpolar amino acid side chains. A reminder, a nonpolar amino acid has an R group that is hydrogen, an alkyl group, or some sort of aromatic, and that R group is always neutral. It cannot acquire a positive or a negative charge. Not to say that the amino acid is neutral, right? Because we talked about the idea of Zwitter ions, the idea that the amine group can be protonated to an ammonium. The carboxylic acid group can be deprotonated to a carboxylate, and that's likely to be the case for our typical amino acid. We're just talking about the side chain now, and the side chain for these nonpolar amino acids are not going to be able to become charged. So they're going to be neutral, they're going to be hydrophobic, they're not water loving, they can't hydrogen bond with water, they're nonpolar. We see sulfur there in the one case for methionine, we see nitrogen there in the tryptophan, but they're buried fairly deeply in and not too available. At least in the case of the sulfur, it's got CH2 group on one side, CH3 group on the other. Its lone pairs aren't terribly available. Tryptophan, again, it's got that aromatic 6-membered ring fused to that 5 ring with the nitrogen, so that lone pair is not as available as it might appear. So we've got nonpolar side chains in these 9 examples. The one that I am going to point out in particular here is glycine, the very first one at the top left, because it's our only achiral amino acid, right? If we're looking at that alpha carbon, the carbon that bonds always, in the case of an amino acid, the amino group, the carboxylic acid group, and the hydrogen, that 4th bond on that alpha carbon is to the R group, and in the case of glycine, that R group is a hydrogen, just like down below. So we have 2 bonds to the same atom, therefore we're not chiral. We have no handedness. There's no plus minus DL glycine. Glycine is achiral, and it's the only example of an achiral amino acid that we'll discuss. So that's pretty notable. And that means everybody else, alanine being just as simple as a methyl group instead of a hydrogen, well, now that alpha carbon is bonded to 4 different groups, as it is for all other cases of the amino acids we talk about. So that's pretty notable stuff, and therefore we should be expecting to be thinking chirality, and of course in the case of human physiology, it's the L enantiomer, the levorotary form that we actually use. The D form of these amino acids don't work in human physiology. So just another example that we talked about that earlier with the D sugars working and the L sugars not working. So now with the amino acids, it's the reverse. So just something to keep your mind thinking about chirality and be on the lookout for here in this chapter. Okay, so moving on to the polar neutral amino acids. So these are much like the nonpolar ones that we talked about, which were all neutral. These are all neutral side chains, although they do have polarity to them. So they're going to interact nicely with water. They're going to be hydrophilic. And so we see these are going to involve R groups that are either alcohols, thiols, or amides. So we see examples of all those. And just like we highlighted the glycine on the previous slide for being the only achiral amino acid, we'll highlight cysteine here because it has the unique feature of having that available thiol group, right? Methionine had a sulfur buried in it, but the cysteine has an SH group at the end of its R group, and that allows for the formation of disulfide bonds. So cysteine, I think we already talked about those disulfide bonds, and we gave the example of permanents and hair, and it's very significant that cysteine can do that behavior. So none of these gain positive or negative charges on the side chain, but cysteine can behave very strongly by making a covalent bond, a disulfide bridge between two cysteine residues. So, and they're not normally neighboring residues. We'll talk about that. Proteins fold in all sorts of complex ways, but cysteine is one to look out for, because when you see cysteine residues, you should be thinking of the disulfide bond being possible. Okay, so we talked about 9 examples of neutral nonpolar amino acids. Now we're down to 6 for the neutral polar amino acid side chains. Okay, so now we're ready for our last batch, the amino acids with ionizable R groups. So we can have either polar acidic R groups, which can become negatively charged, and polar basic R groups, which can become positively charged. And so if you notice, we talked about 20 common amino acids. Well, the biggest group were those neutral nonpolars, right? We had 9 of them. Then we had 6 of the polar neutral side chains in the previous slide. Now we've got our last 5. So of the 20, 15 are neutral, and then only these last 5 are ionizable, meaning they can take on a positive or negative charge. In the case of the acidic side chains, we have just 2 examples, aspartic acid and glutamic acid, and aspartame is an artificial sweetener that involves aspartic acid, as its name suggests. Monosodium glutamate would be an example of a common food additive that has the glutamic acid residue that's in its ionized form, which is why we say glutamate, and that gives a sort of savory type flavor, richness. That's why it's added, although it can also give some people an unpleasant headache after if they've consumed too much. But we have just those 2 examples of acidic with carboxyl R groups, and again, depending on pH, those R groups may or may not be charged. And then finally, we have 3 of the basic with the amino R groups, and those would be histidine, lysine, and arginine. So there we have it. Those are the 20 common amino acids and the particular grouping that they fall into. Okay, so now that we've discussed all those different R groups, it's time for a learning check, and this time we're going to identify each of the following as a polar or nonpolar amino acid. And generally, we denote polar as a capital P and then nonpolar as capital NP. So look at glycine in A and threonine in B, and decide to which type of group you would classify each of those particular amino acids. Stop the video here if you need another moment to do that. When you're ready, start back up and we will check your work. Good luck. Okay, and so you didn't need to memorize the names. I just happened to give you the names because it's important that you begin to recognize these amino acids. But for A, it's really just the side chains that matter, for A or B for that matter. In the case of A, glycine, that one that we talked about as being our sole achiral amino acid of those 20 common amino acids that we'll discuss frequently in the course. It has the 2 hydrogens, the R group hydrogen plus the hydrogen on that alpha carbon that all amino acids share. So it is indeed, in addition to being a achiral amino acid, it's also nonpolar because its R group is a hydrogen. We said hydrogen, alkyl group, or aromatic would get us nonpolar behavior. For B, now we have some carbon groups there off of the alpha carbon as a part of our R group, but the most important feature that we see there is that OH group. So that OH group gives rise to an amino acid that is indeed polar. It's going to be able to hydrogen bond with water as a result of that side chain, and therefore we would classify threonine as a polar side chain. And if we wanted to get really technical, although this particular learning check didn't ask for this level of detail, we would call that a neutral polar side chain. So there you have it. Hopefully that's what you assigned, and if you didn't, or you're not sure what we did here, please do reach out to me for some help. I've made a big deal about glycine, right? Hopefully you caught that. I've tried to intentionally make a big deal about glycine because it is a big deal that glycine is our only achiral amino acid. That means we have to be able to deal with the chirality of all those other amino acids. And so the way that we show amino acid stereoisomers, much like what we did before for looking at the carbohydrates, is we do Fisher projections. And so these are Fisher projections of amino acids. So, as I said, amino acids are chiral with the exception of glycine, which has two hydrogens on the alpha carbon, the hydrogen that they all have, and then its R group is a hydrogen. So, for the amino acids, then we have Fisher projections that are stereoisomers. And so we have L isomers being the type that are actually used in proteins. The D isomer exists, we can make it. It just doesn't do anything in the human body, but as chemists, of course, we can make pretty much anything. No egos there, right? You haven't caught on at all that the chemists are a bit egotistical, thinking that we can make and do anything. But of course we can, pretty much. So there you have it. So the L isomer and the D isomers differ in how they're shown in the Fisher projection. So by convention, the Fisher projection will show the carboxylate group up top, the R group down at the bottom, and then depending on how you see that central grouping there, if we have the amino group, which is typically, as we said, for the Zwitter ions in terms of the amino acids, it's typically a protonated ammonium. If that's on the left, then we have the L isomer. If that's on the right, then we have the D isomer. So that's goes back to our glyceraldehyde. If you remember, we said the alcohol group on the left gave rise to the L isomer, and then the alcohol group on the right gave rise to the D isomer, because that hydrogen, whether we're talking about the amino acids or the carbohydrates, the H is just not as high a priority group as either the alcohol or the protonated amine. So there we have it. That's how you can use Fisher projections to differentiate the different amino acid stereoisomers. So on that note, we'll close our initial discussion of amino acids, and we'll move on in the next lecture to further discussion of amino acids and proteins. Hope to see you then.